And now we are going to do some examples. Sample 1. Determination of the activation energy. Calculate the activation energy for the decomposition of benzene diazonium chloride to give chlorobenzene and nitrogen. Using the information in table E3/1.1 for this first order reaction. So here we have the table in which in the first row we have the rate constant in seconds to the -1, and in the second row we have the temperature in degrees Kelvin. We start by recalling the Arrhenius equation, in which, if you remember, it was established as the natural log of Ka, the rate constant, is equal to the natural log of the pre-exponential factor A capital minus E divided by R, where E capital is the activation energy and R is the gas constant, times 1 divided by T. We can use the data in table E3/1.1 to determine the activation energy E capital and frequency factor A capital in two different ways. One way is to make a semi-log plot of K versus 1 divided by T and determine E capital from the slope. Another way is to use Excel or Polymath to regret the data. The data in table E3/1.1 was entered in Excel and is shown in figure E3/1.1, which was then used to obtain figure E3/1.2. So here we have the figure E3/1, in which we have the different values of K in the in the column number 2, we have different values of K that go from 0.00043 to 0.00717. Then we have the natural log of these values of K, which goes from -7.75 to -4.94, and in the fourth column we have 1 divided by T, temperature in Kelvin, to the -1, and the values go from 0.00320 to 0.00300. So we can make a semi-log plot directly from the second column and the fourth column. And here we have, if we use the values of A, which are of column A, which are the rate constant, and we use the values of 1 in T, which is the column C, we will obtain the plot at the left, which is the plot of the figure E3/1.2a. And if we take the natural log of K, and we plot it against 1 divided by T, so we will have the plot on the right side. So those two different ways of resolving this problem will lead us to the same result. And here we have the graphical solution. In figure E3/1.2a shows the semi-log plot from which we can calculate the activation energy. We rearrange the equation of the Arrhenius at two different temperatures. Log of K2 divided by K1 is equal to minus E divided by 2.3 R times 1 divided by T2 minus 1 divided by T1. And this is, if you recall, is applying the Arrhenius equation to two different temperatures. And that's the expression that we have. From here, we will have that the E capital, the activation energy, is equal to minus 2.3 R log of K2 divided by K1, all that divided by 1 divided by T2 minus 1 divided by T1. So we can use values in which K2 is equal to 0.1 K1. In that way, we will have that the log of K1 divided by K2 is going to be equal to 1. Then, when K1 is equal to 0.005, 1 divided by T1 is 0.003025, and when K2 is equal 0.0005, 1 divided by T2 is equal 0.00319. And those values we get them from the figures in the previous page. So if we do the calculations, we will come to the value of the activation energy equal to 160 kilojoules or 28.7 kilocalories per mole. So from the Excel analysis, when we plot the natural log of K against 1 divided by T, we come to a value also of E equal 116.5 kilojoules per mole, which is the same value that we obtained in the semi-log plot, and we can have that the natural log of the pre-exponential factor A is equal to 37.12, from where A is equal to 1.32 times 10 to the 16 second to the minus 1, and this is the same value that we got it in the first plot, in which K is equal to 1.32 times 10 to the 16 minus 14,017K divided by T. That will be the expression for K at different temperatures.